Okay, so plan for today is that we try to implement this Leiden algorithm, no, the Louvain algorithm, whatever the older one of the two. And the idea behind was it to get a bit started with some programming, also for me to have a bit a feeling of what your level of programming skills or previous experience is, and last but not least, simply to try out how this works to make a sort of collaborative programming project in on the screen like this. And what I now want to do for this, as you might remember from Monday, we wanted to implement this Leiden thing. I've prepared some example data and I found a nice collaborative Python platform where we can all edit the code together. I have no clue whether this will work, but let's try it. So, to see where we were last time here, I just put together the code we had last time. We read in this matrix. I won't press it again because I've just read it in this morning and it takes a while to read in this big file. When, as you remember, we log normalized, we got the most variable genes, we made this log transformation when we made a PCA and a UMAP, and here was the plot of this UMAP, and each point is a gene. And now, in order to have a simple example so that we can quickly try out our code, let's reduce this down from currently 14,000 cells to only 1,000 cells by taking the sample function in R, where these are just here all the barcodes of our cells, and I randomly now select 1,000 of them. I again call this function, this k nearest neighbor function to get, let's make it only the 10 nearest neighbors, also to have it easier. And now we first, so that we know what the proper solution is, I start with the, I run the iGraph Leiden clustering algorithm that we had before, and now you remember what you then get is this vector which gives to each of our 1,000 selected cells one number for the cluster. And I can plot this here by just taking the UMAP coordinate of 1,000 selected cells and the membership. And now you can see here, it's now only 1,000 points, and here you see the colors, and that's the cluster it has assigned. Now I've written this here onto a table. So what I've written in this table here is this thing here, which tells me for each of 1,000 cells the 10 nearest neighbors. And importantly, because we will now switch to Python, and R is a one-indexed programming languages where the indices of all arrays start with 1, but Python is 0-indexed. So all our index, what used to be cell 1 is now cell 0. So I already subtract 1 from all the indices so that we can start right with correct indices in Python. And I also save the UMAP coordinates and our sort of solution from R in this table here. So you see that would be that table that just gives us here for each cell its barcode, its UMAP coordinates on this plot and its thing. And now we can switch over to Python, and now comes the part which I'm wondering whether this will work. So I've discovered a tool called Replit, which is a collaborative coding platform. I'm already logged in, it seems, here, and now I say I want to create a Replit, a REPL, which seems to be this coding, and let's call it graph modularity. I can't make capital letters, no. Okay, then let's make a minus in here. So, and yes, no, it wants create a Python template, and I want to call it graph modularity. And now I create this REPL and upload my 2 example files that I have here. Or now the way how this now works is I can write here some Python code, and if I then click run, when it executes it and shows me the output over there. And the nice thing is I can now click somewhere here on share. Where is that? Deploy, probably this thing here. 9. Deployments. When I did this morning, there was a share link. Maybe it's this invite here. Private join link. Copy join link. And I put this on Moodle now. And then you can all join my project. Okay, Moodle. Cursor. Here we are. Material hinzufügen, URL cell, Replit join URL, and here we go. Speichern und zum Kurs. So maybe everybody give it a try. Here I've put it, I called it Replit join URL, and see if you can join my course here and see what I'm writing here. And the point is now, if I now here write something, I think you should see it live changing on your computer. And I think it should also be possible that you now enter something. I hope I put this link on copy join link, private join link. Yes, I hope I made it here that everybody can you try, can somebody who's already in there try to edit the code? Okay, yes, this works. Now, obviously, unless if it's up to you, I don't know if you've used an anonymous or a, those of you who have used their real name, you now, of course, everybody will see whether it's clever what you write here. So what I now do is that I first upload the 2 files I just had. No, not like that. Upload file. Temp, that was this one here. And upload file, and what the other one, the UMaps CLV. So now I make, let me try to read in the neighborhood file. Import NumPy, SNP. Has everybody worked with NumPy before? Who hasn't? Okay, then you'll figure it out while we go along. There also seems to be some AI assistant which also helpfully adds some random stuff. Let's see, it thinks that the next thing we need is Matplotlib, but I now want to read in this file here. I also have my helpful coding assistant. Of course, you are hopefully more helpful than this one here. P read matrix from CSV file. Because I can never remember all these little things here. Let's see if this works. And right, installing NumPy. It first needs to install this, but at least it thinks for us and does that. So it seems we have some online CPU here, some online virtual machine which runs our code for us. And if we are a bit patient with it, it will run for us. But what has it now done? Stop. Maybe I shouldn't have printed the whole thing. Here we get a price book file name.csv. Yes, this wasn't too intelligent. I called it, so that's now your job to notice if I do something stupid like this. And seems to be a tad slow, this thing. Probably we have to pay for it in the end to use this. Or I switch over to a, okay, now this works. And now the first thing I want to do is, I thought in order to work with it, we should get a good data structure. And this is already looks like a halfway decent data structure, but it's not ideal because what we'll later need is to be able to tell for every vertex in our graph what neighbors it has. And there's classically two ways of looking at of describing a matrix. One is the adjacency matrix, and the other is the edge list. So let's introduce some notation. Where's anybody sees the chalk? Here is a tiny piece of chalk left. So we introduce adjacency matrix A Aij is 1 if edge ij and 0 otherwise. This is one way to do it, and the other way is that we make an edge list where for each vertex we have a list of its neighbors in the graph. And we will later see that the edge list is more useful to actually program, while the adjacency matrix is more useful to derive what we want to program. So we first make the edge list, and I make the edge list by just making a list. I call this now here an edge list. And in this edge list I start with an empty list, and now I go through the vertices. So for v in range nn dot shape 0. I hope this is the number of rows of nn. Or maybe we can do this as our first little exercise. Everybody who wants to can make their own little code here, or you run it on your own computer. But our first job is to make a list which looks like this. And we make this not as a NumPy array, but as a Python list for now. 3, 5, 2, 2, 7, 10, 11. So, there is for each vertex there is a list, and the list contains all the neighbors. That's the first thing we quickly need to program. And I think now, because this thing can be slow, what I now do is I open a Python on my own computer. And you can do the same, and quickly let's try to find code to make this. PyEnv, no. Student, ich nehme hier mein Sublime File, New File. Tools, terminal, system. Where's my terminal? View, show console. Oh, let's do it like this. So obviously you can try to not sneak what I'm writing because I'm trying myself. Try it yourself, but just so that you can get started, we can also sneak. And I switch off my screen for a moment. Found a mood button. List V and then so if somebody has a working edge list thing, they can copy it over into the code box. In the meantime, I will write down the next formula that we need. I already prepared for the next step. So we'll leave this in a moment. But first, who has already an edge list? Good. Who else? Okay. So what turned out to be the challenges? Let's see. Let's look at who has half an edge list, when we can look at their code and try to continue from there. Okay, so but maybe so that we go on, I show you my solution. So this here is my solution. I hope it's right. I'm not 100% sure, but that's what we came up with. So what I did is I started here with, I went through all the vertices here. Maybe I copy it over to the other thing, then you can just read. Now let's just show it here. I go through the vertices. So you see this is our neighbor list, and shape is the dimension. So shape 0 is the number of rows. Shape 1 is the number of columns in our NN matrix. And we go through all the rows. And now I have my edge list, and it's a list of lists. So I initialize it with an empty list. Then for each element, I first add an empty list to my list of lists, and then I fill this empty list by adding the entries here. And the trick here is to remember to always first put in empty lists, because if you don't do that, you run into, well, obviously, yeah, it seems clear that you have to first initialize the list and then we fill it. And in the end, once I have them all, I run it, and if I run that, this is what I get. I quickly put this over in our collaborate document, and as you can, it uses two. Okay, so, and every code clear to everybody so far? Is this roughly what you had? What are those who didn't manage? What was the gotcha that you stumbled over? Because if you haven't programmed with Python for a while, or remembering this, that you first have to create the empty list and put it in, it takes a moment. Important also here, this thing which I forgot on my first thing, of course some of these edges appear twice, because with if one cell is neighbor to another cell and it's in reciprocal neighborhood, they consider each other neighbors when they appear twice, otherwise they appear only once. So the next thing we want to do is we want to understand this, see what the modularity is. We first want to simply calculate and see if we get the same modularity that we also got here, where the R function told us the modularity is 0.760. And for this, of course, we need an assignment of edges. So let's quickly load the other thing. How does this, anybody remember how this works with pandas? Pandas read CSV. Let's try it like this. Now, import pandas as PD, and now I make here at the bottom panda.read CSV and read in the other list umap cl.csv. That's why I don't get a connection. So, and print table, I call this so that I see if this works. And then get column as number think is I simply take it out as a. Okay, this is slow, so I better put this over in my own thing here. Print edge list. Import pandas SPD. ls ump is what I called it. So now I want printable dot group dot values. Okay, so this we seem to have. So I have my edge list, I have my tibble, and now I want to make a function calc modularity, and that gets the edge list and it gets the group assignment. So tibble group point values, and def calc modularity edge list, comma group. So, and in order to calculate the modularity, what we now have to do, so sorry that it's not that very good, maybe it becomes better if I explain it next time I write bigger. So, we first, you remember how we defined the modularity here. If not, I quickly remind you. So we start off by saying the adjacency matrix is Aij, and I will use G of I to say which group is vertex I. So this is our group vector. And then I calculate the number of within group edges. So how many of all the edges are within the group? And in order to do this, what I have to do is I go through all the vertices and through all the neighbors of these vertices. And then I now have here, so this here is a sum over all the vertices, so we run it simply from 1 to n, and this is a sum which runs through this specific, through the neighbors of vertex I, j element n of I. And then for each, and then of course we now know that there's edges I and j, and for each edge I ask how many, I ask what group is I in, what group is j in, and if they are the same, I count this as 1, otherwise I count it as 0. And that should give us the total number of vertices, of within group vertices. And let's see whether we get this. Actually, is it? There's one mistake that I've just noticed while explaining. Who sees it? Yeah.
You have to leave out vertex I when you count the neighbors?
This depends. I mean, this year we go through the vertex, through all the neighbors of I, and I think the way how we just constructed the table, it doesn't contain the vertex I. So it's just about how we understand this. Who sees it? Otherwise you can start implementing, and then while implementing, let's start it. So the first thing that we now want to make is a function which calculates the number of edges, the number of internal edges, and divides it by the total number of edges, so that in the end we get the fraction of edges that are within a group, so the number of internal edges divided by the total number of edges. And for this, now that you have your edge list, let's calculate. Let's see that.
Let's say we want here
fraction of internal edges. So,
I have a question regarding the edge list.
Yeah.
We introduced the second layer of lists. Why did we do that? Could we skip that and just make one long list with all the edges?
yes, but where do you know which edge belongs to which vertex?
I thought we write both values, like vertex 1, vertex 2.
Ah, no, what I have now here done is I made it such that you see it looks like this here. It gives me for each vertex, it gives a list. So I read this out, this list of vertices.
Okay.
I read it out as, let's try this here, print edge list. So I could, for example, make neighbors of edge of vertex 17, edge list at 17. This is how it's supposed to work. And the reason we will later see that this is advantage, and that's actually a crucial point if you want to program something like this. You have to think hard about what might be the best way to store it. Because when I thought about how to show this was also my first idea. Let's make a list of pairs. And then I realized that it won't work. The reason why this will not be suitable will become apparent later. So I've tried to think ahead what might be the right thing, but in practice, usually you start programming such things and then you realize actually it's the wrong data structure, and then you start over. So who has already written here the number of, has found the fraction of internal edges? I let you try a bit while I do the same here. This was not good. So who's getting ahead? You have a nice fraction. What is your fraction?
It's 97.4%.
That's what I have too. Anybody else getting close to getting a number? And what I will now do is, I think I will now show you how I would develop this slowly, or just recreate what I've just done. Now pretending that I haven't thought about it yet. Why is this all blue? Somebody has marked everything here. Okay. So now what I now want to calculate here is this fraction of internal edges. So I make here my function and fraction of internal edges. Now what I obviously have to do is I have to make these two sum signs. So I run through the outer sum. I make a for loop and I want to, how does it, wow, range len edge list. Or somebody else already typed this. This is exactly what I want to type, what the AI here says. I want to run through, I now say this is my edge list. The length of my edge list, that's all the vertices. And if I make a range around that, something like for v in range length edge list, then I go through all the vertices. Because each vertex is, because we now run through the indices of the vertices. And now, of course, I can get the neighbors of this thing. If I now look at edge list v, that's the neighbors I have. I call this neighbors. And this is now a list which contains all the individual neighbors. And now the next thing I do is that I go through these neighbors and get the neighboring vertices. Let's call them w. For w in neighbors. This now I have this v and w. These are edges. And I check whether they are in the same group. So group egg v. This is the group in which the edge v is. And this here, group egg w, this is the other group. And if they are the same, then we have found an internal edge. And I count this by saying n internal plus equal 1. Obviously, I have to define this counter by putting here something like n internal equals 0. And now I run through the whole thing. It runs through all the vertices and for each vertex through all its neighbors. And then it gives, and whenever it finds an internal vertex, it adds 1. If I now make also n total, I also get, because in the end I want to give back the number of vertices on total. So I want to return something like this fraction. Return n internal over n total, because, and for this of course what I need here is also a counter for the total ones. So, and now I can check whether this works by printing that, what I get back here. Then we call this group. Group gleich. What did I just have here? And okay, what did I have here in the meantime? It tells me here, there is a parent missing. And it says something about an indentation error. That should be right. Anybody sees any mistake here? Edge list maybe. It's now okay. Space is 2. It's too few for me. Save and re-indent. So, does it now do what we want? I hope so, at least. Here it complains about something. Okay, while we wait for this thing, which is obviously too slow if one is not using the paid plan, we can already think about the next issue, namely, for the modularity we have to subtract from this fraction of internal edges that we actually have, and we call this actual fraction. Actual fraction. And then we also want to get the expected fraction under random permutation. Expected fraction. So this is the expectation under random edge permutations, or if you randomly permute the edges. So we take for each. And you remember how we did this? We go to each vertex, and for each vertex we ask pick new neighbors and pick them randomly. And then how many edges will you get? And now for this to see how many edges we then get, we can calculate that we say expected a fraction of internal edges under random reconnection. And what we thought about this last time is this essentially we can ask for, what was our reasoning last time? For each, in order to calculate this expected fraction, we can ask if we pick an edge at random, what is the probability that it connects two vertices out of the same thing? And in order to do this, what we do is we say probability that let's first the prob that randomly chosen edge starts in group G. And this probability is, as you can imagine, we just have to see how many edges start in group G and what is this among all the edges. How many groups start in edge G? For this we have to add up the vertex degrees in edge G in group G. So we have to introduce something which I call NG, number of edges starting in group G, which I call NG, and this is the sum over all the vertices in group G, and we add up the degree. And this is, so this is just the number of neighbors for the vertices. So for each group we can calculate how many neighbors do all the vertices have added together. And once we do that, then we can say the probability, if I chose a random edge among all the edges and ask, does it start in G, is of course given as the number of edges that start in G divided the number of edges that I have in total. And the probability that it also ends in C is the same. So the probability that it starts and ends in G is the sum of this, is the product of this. And the probability that the edge is internal is we have to sum this thing over all the groups. And then we get the number of, and then we should get the probability that an edge is internal. So let's quickly program that. Expected fraction, for this I need to now to know for each group how many edges it has. So I ask first what is the maximum of group, to know how many groups I have. And groups is group.max. I hope this works. No module called pandas, huh? This thing doesn't have any pandas installed. That is annoying. Okay, so I first see if this actually works. Print group.max, whether this actually gives me the number of groups that I have. 7. Now I wonder what's my groups. I should now think for a moment about it. I number them from 0 or from 1. And it seems I numbered them for 1. So I better fix this by subtracting 1, otherwise I keep getting confused. It's 0 now. So now I can, with this logic, I can now say, this here is I call the actual fraction of internal edges, and this here I call the expected fraction, expected under random things. So, and n groups is group.max, now plus 1 because I've just decided to start running from 0. And expected. What's the next thing I now need to do? Now I can, now that I have this, I can make a list to get this ng. Edges per group. And for this, I just initialize an arrow of 0. So np.zeros. And yeah. So now I have an array of zeros, and now I can go through all the edges, through the edge list. So for v in edge list. And now what do I have to do now? Range len edge list. If I now am at a vertex, I can first check which group this vertex is. Group v tells me which group we are in. And so this is the group of the vertex. And the other thing, we can ask how many edges start at this vertex. And that is, of course, a moment for everybody to think. Everybody has thought. So I can resolve, or who tells me how do I get the number of neighbors that this vertex has. How do I get this vertice's neighbors? Yeah.
The length of the edges.
Exactly. Edge list. That's the list of edges, and this here is the neighbors of v. Actually, it might have been better if I had called this variable not edge list, but a neighbors. Then it would be easier to read. This is the neighbors of v, and the length of the neighbors of v tells us the degree of this vertex. And this we have to add to this edges per group. So I say here, edges per group, and to this add this length. And here, let's call this the group. And then I have now for each thing here these edges per group. And now I can calculate this formula, which tells us we should go through these edges per group for I in, or let's call it G, in range. Actually, this is a NumPy thing, so we can now very simply take this here as edges per group. And I want to divide it by the number of edges that I have in total. This is the number of edges I have in total. And if I write this here, let me see if this works actually. IPython, before I import numpy as np, np.array. Let's say you have a numpy array where the first group, say, it has 13 edges, the next has 37, the third has 15, the fourth has 22, and the fifth has 9. So I have something like this. And now what I want to do is I first want, so this is the number of edges of each group, and in total I have 96 edges. If I now divide A by this here, then I get these fractions here, the number for each group by the internal number. If I square it, I will next square them. I'll square. No, sorry. Times, yeah. What does this thing here do? I'm missing a parent. So, and now I can sum this up again. And I get the expected number of edges for this thing. So let's copy this here. So edges per group divided by the sum. This whole thing squared. And summed again. And that should be the result. Return it. So I now make here print actual fraction and print expected fraction. And now I get here 0.97 and 0.21. And if I subtract the two from each other, I should get my modularity score, which I suspect I don't, because our modularity score is 0.76. Ah, yes, this might work. So, then I print also the difference between the two. .7636. So, first achievement, we have managed to recalculate the modularity score that the function from the iGraph package has given us, 0.7607. 0.7607. Control A, C, quickly copy this over to here. And now the next thing we can now do is, even though we're probably slowly running out of time, is we can now try to optimize, because you remember in the modularity score algorithm, the usual algorithm was that we start with something very simple, namely we give each vertex its own group. And then we try to calculate the modularity score. So let's def modularity score. Edge list, group, double point, and this is simply return expected fraction, actual fraction, edge list, group, minus the expected fraction, edge list, group. So this is the modularity score, and now let's do the following. Instead here print modularity score, edge list, group. See if it still works. Alt here. Minus, doesn't like that. 0.76. And now I try this simple thing that I initialize group to something stupid, like numpy.arange. Now I put each thing in its own group by saying len edge list, and see what the modularity score would be with this simplified thing. And you see when the modularity score is even negative. And now we try to optimize that. And we first do it the stupid way. The stupid way to optimize it is that I simply take a group, that I take each vertex and try to improve it. So I do the following. And this is now Leiden algorithm the wrong way. And then we do it the right way. So I go through the vertices. For V in len range len edge list. And now I say, which group should I put this vertex in? And I try all the possible groups that I have. And I think we should keep track of the groups we actually still have, because occasionally we might lose groups. So at the beginning, I make here a list of n in group, so number of elements in the group, np. Can I do repeat or something like this? Does anybody know how in numpy ipython import? I now want a lot of ones here. np.ones 10. Yeah. So n in, and I want this is integer. D type is np.int. Int doesn't like that.
If
Integer.
you remove it, you can append .sint.
Hmm?
The d-type integer doesn't work, but if you remove it, you can do .s type and then...
Okay, but now I got it with the int that also works. So instead, so let's see, and now I can put it like this. Say I have now how many edge len groups, and also len edge list. So for each of these groups I now have, each group has one element. And what I can now do is I go through these here and check for each vertex what happens if I put it into another group. So I go through them for G in group. In again len n in group. And now I ask, do things get better if I put G into this group? So I temporarily change my group thing by saying the group of a vertex V should be G. And I ask, what is the modularity score now of edge list, group? And now I'm trying to find which group do I have to put this vertex to optimize the modularity score. And for this, I check what is my best score so far. So I say best score is, and at the beginning the best score is, let's say, do I have an inf? I think I have an inf. No. Actually, the modularity score can never be smaller than minus 0.5, so I simply initialize with -1. And now I ask here, my new score is S, and I ask if S greater than the best score we had so far, when S is best score and best group gleich -1, and the other way around, best score is S and best group is G. And now the way how this works is we go through this, we try now for each vertex what it is, and in the end, when we get out of this, we now say, actually I shouldn't yes, let's leave it like this. And now once I'm out there, I say, okay, this seems to be best thing, so this is what we now leave. Group V is best group. And then we print what our modularity score is now. And one thing I have, and now let's just start it that way. Yes. See if this works. Edge list. Where is this wrong? Line 47 here. I have no clue whether this will work now. But int is not iterable for G in rangelen. And function modularity score. This is not best score is what I wanted to print here. And as you can see, this is slow. It goes through each vertex and now it optimizes vertex 1. So maybe I put this here, print optimizing vertex, comma 1, comma V S. And it doesn't even work because it gets smaller and smaller. 1, 2.006. 0.004, yes. And what you can now see is for each vertex, and now we are coming to the trick of the Louvain algorithm, because as you can see, this is terribly slow. And why is it slow? Because we have this modularity score function which has all these loops. And now for every group it has to go through all these loops, and that of course takes ages. And we still haven't really managed, we've just reached a score vertex 10 and it doesn't really get much better. So we need to optimize this calculation, that we don't have to recalculate this. And that's where now our trick comes in, namely, where is the wiper? How does the modularity score change if we move vertex V from group G to group H? And to do this, we first look here at the number of actual matrices. What changes here? The total number of edges that are in the same thing. So the number of edges, the number of internal edges, Ni, the new Ni, so the new number of internal edges is the old number of internal edges plus, and it can change by 1, 0, or minus 1, depending on whether the vertex has before been, sorry, no, not like this. So what we now have to do is, when we move the vertex, we have to ask how many edges change their status from having been internal to now no longer being internal. So we have to go through this vertices edges and ask for each edge, was this an internal edge before? Is it an internal edge now? Did its status change or not? So Ni changes is the new, is the Ni plus, is the old Ni plus number of vertices of neighbors of V that so all the neighbors which before were also in the which before were not in the group that were that before sorry if a neighbor is in G, that's it. If a neighbor is in G, they are in G. Because if a neighbor is in G, when the vertex was connected internally to this neighbor before, and now if we move it into the other group, it's no longer. So minus that, plus number of that are in H. So we can very easily calculate how the number Ni changes by just going through the vertices only of the neighbor V, of the edges of the neighbors of only of the neighbor V, and ask how many of these neighbors have before been in the vertices old group and how many are in the vertices new group, because that's the number of internal edges we lose and that's the number of internal edges we gain. And the next question we have to ask is, how does this thing here change? To make this easier, I first calculate out here Ni squared sum over Ng squared. So this probability that something changes internally, that thing here, Ng squared, so this here, this sum of Ng squared that we have here, which we have in the second term, changes to, and you can easily imagine because of course this is let's call it Ng prime, because this is now prime. And here we add, of course, because Ng now gains one count, loses one count, and Nh gains one count. So we have all these groups here. G1 squared plus G2 squared plus, and now at some point comes this group G, which now is reduced by 1 squared, and the group H, which now gains one vertex. Sorry, it doesn't gain one vertex, but it gains all the vertices of this thing, squared plus, and now comes the H here, vertex of group H, and so on. So this changes, all the groups stay as they are, but one group, namely the one we are leaving, is reduced by this, and the ones we are gaining is added by this. So the net change is Ng1, Ng2, Ng, Nh, and so on. The net change is Ng squared stays as it is minus 2Ng dV plus dV squared minus 2n plus 2nh dV plus dV squared. So the net change overall is is done this right now, plus should be, if I calculate it correctly, 2 times the degree of the vertex squared plus 2 the degree of the vertex times nh minus ng. And this is now the trick in the Leiden algorithm, when we want to see what changes if we move one vertex from group G to group H, we don't have to recalculate the whole modularity score. All that we have to say is the first term of a modularity score changes by this here, and the second part of the modularity score changes by this here. And this, of course, is quickly done. Here we just need a very small for loop which goes once through the neighbor list of vertex V to check how many are in group G and how many are in the group H. And for the net change, we have to do, and for the net change of the other term, we just have to calculate here the degree of the vertex group and the number of things which are in this and in that. And now you can see all that we have to do is that we have to keep score of this NG and NH, which in our code is this thing here, with edges per group, and then we have to try what happens if we change it, if we increase this by 1 and decrease that by 1. And in this way we can calculate and find the optimal thing, and then it will be quite fast. Now it's 39 officially, we still have 5 minutes left. I don't know if we can implement this in 5 minutes. I'm also not sure if it's worth it. For those who want to practice their programming languages, their programming skills, this is a voluntary homework. And you can see there's two things about if you actually want to do that, and I think if you actually want to get more proficient in numerical programming, that might be quite helpful to try this. There's a couple of things you have to do if you now want to try to speed up our Louvain algorithm just so that we get a quick result. You see we still are nowhere near a good optimum, and that should happen in 2 seconds. The first thing is, of course, double check my reasoning here, because I didn't look at my notes, so I'm not sure whether I said this right. Especially, I'm very suspicious of this 2 here. It feels wrong. The second thing is is then think about how you have to rearrange all the code, because at the moment the modularity score is split into this and that, and maybe you need to write a new function which then calculates once this thing and that thing, and then goes through all the vertices and checks what might be the right way. And then once you do that, you come into all kinds of other little things that you might notice. What do you do with groups that vanish? What do you do with and finally, which is the last thing we will have to do, is find out how we optimize the whole thing, because we are using Python. And Python per se is a bit slow. And there is these ways with just-in-time compilers for numerical stuff. I don't know if anybody here knows Numba, which allows you to make Python code really fast once you have assured that that your code only uses primitive types like standard scalar types, NumPy arrays, Python lists, and Python dictionaries, and then suddenly you can speed it up by a lot. Maybe we try this in the exercise next Wednesday. With that, I would ask you to, depending on your mood, you can just try to do this yourself. You can just wait for me to do it and show the code where I implement this next time, and then say, yeah, obviously this is what I've already also done. I can do the same and just not do my homework and hope that one of you do it. And then I can show you next Wednesday how we optimize the code and how we use this Numba framework to make sure that it really gets as fast so that we get our result. You remember with the I function out of the iGraph package, we got a result within less than a second, and we want to achieve the same, and I think we'll get there and we'll manage to do that. And then you have a very nice example of how to implement an algorithm out of combinatorial mathematics or concrete mathematics in a very fast and efficient manner. And this is, I mean, I'm now here heading it with dual learning goal of A, showing you how you apply mathematics in biology, but also of making this as an example to practice how to actually implement mathematical algorithms in a manner that you can practically use them. And yeah, I hope this will turn out to be useful, and let's see how far we go. Yeah.
I don't know if this is too restrictive, but wouldn't it make more sense to move nodes to just the neighboring groups instead of checking every possible group?
This probably it's too restrictive. So first, I mean, I'm just implementing what the people from Louvain has suggested. The reason why I think it's too restricted is because there is no topology. Our groups are just numbered. There's no reason to imagine that two neighboring groups with neighboring group numbers will be close to each other. Also, what you remember, we start off here with 1,000 groups, and in the end we have 7 groups. So we will very quickly notice already after going through for the first time, probably most of the groups will vanish, because for most vertices we will add it to another vertex. So we'll quickly go down from 1,000 groups to only 10 groups after the first epoch of going through all the vertices once. And then it probably makes more sense to look through them all. You might know the bubble sort algorithm, which is the traditional example of something where you always only swap with neighbors, and it's also the traditional examples in an algorithm class for an algorithm which is unnecessarily slow. So this is why my gut feeling was that this won't work what you suggest, because it sounds like bubble sort and probably shares its issues. Other questions for this? It was just for me to get a feeling about this. As I said, I fully expect that the coding experiences that you have are a bit mixed. So but of course this is all a matter of practice. Did everybody have a feeling that you sort of were able to follow and understand the code that we've developed here, and will be able later to sort of practice to do this yourself? Then I think we'll get ahead slowly. Yeah, what do I now do? I think I quickly take here my slow code and copy it over here in that one. So if you want to, you can quickly crop out this thing, and our test is to improve this here. And of course, what we also need is better make a picture of that for myself, because I also will need this, and I have a strong feeling that there will be definitely a few mistakes in this. Especially one thing I'm very suspicious of, because nobody has noticed, is the issue with a factor of 2. There is always this here. I correctly remember that every edge that appears in my edge list appears twice. Once is edge from I to j, and once from j to I. And also all edges appear twice in our edge list. And that's why I've divided by 1/2 here. Here I've forgotten that, which is why this here is wrong. Luckily in our code I've forgotten both divisions by 2, so we can't. And I have a feeling that probably some of these factors of 2 too many or too few on the right half. So let's put this in here. Otherwise, enjoy tomorrow's holiday. I had completely overlooked that. This is for me, I've discovered this only this morning. And on Monday we'll talk about dimension reduction. We might get a bit of out of sync with our programming exercises and the topic of a lecture, but we can do that. So, where is this scanner again? the power supply fried the processor. I ordered a new processor which might arrive today, otherwise on Friday. So on the weekend it should be up again.
Bye.